Okay, we're now recording. Okay, we are very, very lucky and honored to have Gunnar Grosch. Am I saying that name? Am I saying that correctly?
That was an impressive pronunciation of my name. I've never heard it better from the US, to be honest.
Oh, okay, awesome. Gunnar has been an Amazon hero and recently became an Amazon senior principal Uber developer advocate, and he gives talks all over the place, and we are very, very lucky to have him here. So, let me give screen share capability.
While you're doing that, Brian, we kind of skipped over announcements and jobs. We'll come back to that maybe.
Oh, okay.
What do you want to do that now?
Let's do it now. Sorry. Yeah, it's funny. I had a sense of missing something. So, anybody have anybody's company hiring? Just unmute and jump in.
You know, I work for a large company, and I couldn't tell you exactly what, but they are always looking for more tech skills. The company is called Perspecta.
Okay. So if you have was that Stephen?
Yes.
If you have a link for the, even just like main careers page, you could post it in the chat, and ideally also go to our Slack and post it in hash jobs. And just say, hey, if you're looking, here's a general list of things, even if it's not a specific role that you're looking for.
Okay.
Anybody else?
I can go. I'm Antal. I work at Drizzly, and so like Drizzly's hiring a bunch of roles right across the board, software engineers to data engineers to ops engineers. So if anyone's interested, we are a AWS shop. So yeah, looking for a good talent. And I'll post a link to our jobs page also in those two channels.
It's great that we have someone from Drizzly here. One of the earlier virtual meetups, I was looking to do a giveaway, and I was all excited. I was going to have basically just deliver beer to someone's house. And I found there's a beer. It's like, I can't remember what it's called, but it's like Cloud something. I was all excited.
Cloud9?
Maybe, no, but it was Cloud something beer, and we couldn't quite get it all to come together.
Okay.
But now you're here. You got to come back, and you got to send beer to somebody.
Definitely.
I live in Saco, Maine, not super far from Boston, and you guys do not deliver beer here yet, or like your sales people don't, unfortunately. It makes me real sad because every time I say like beer delivery, wine delivery, you guys pop up, and then it's not here.
We are working on it.
Okay.
Put in a ticket for that.
Yeah, you're going to make it happen here in Saco now, right?
Yeah.
All right. Any other job announcements?
Hi, this is Kamlesh.
Go ahead.
I work with CVS Health, and we are located in Burlington. And usually we have openings for software engineer, senior software engineer, and principal level, Android, iOS, or web application. I don't know any specifics at this point, but usually we are having many openings.
Excellent.
I can add. My name is Daniel. I'm with Ahead, and we've now acquired a few companies and we're nationwide, and we have 3 openings for senior AWS architects. So I posted a link in the chat.
Thank you.
This is awesome.
And with TraceLink, I posted a couple links there for security and cloud ops. Of other positions, more of a software developer. There's a number of engineering positions as well. So we're a SaaS provider. Headquarters is just north of Boston in the North Reading area, but international offices as well, if you know folks in India. And we're an AWS shop.
Okay, anyone else? And I'm so happy to say that I no longer need these job links because I'm starting a new gig on Monday. So yay.
If there's anyone looking for a job, feel free to raise your hand too and let people know.
Yeah, I know I'm not looking for a job specifically, but I'm actually looking for an internship. I'm a student. Name's Jack Canducci. I'm in the Slack. Yeah.
Okay. Yeah, post in Slack and you know, we'll see what we can do.
Yeah, and I'm looking for a cloud security architect gig.
Robert, let's chat.
We're overdue, man.
Yeah.
Yeah. Yeah.
All
right.
right. It's a quick, I'm sorry, Brian. I just got to quickly say, it's interesting, just as we've been doing these things every 2 weeks through pandemic, this is the most activity we've had on jobs. I wonder if that's a odd sample point or a sign that things are picking up. So we'll see how it goes next time.
Right.
I can tell you guys, since one of my projects is the USCIS, this H1 shutdown has opened up a lot of opportunities. It's like a shortage. So I noticed that there's a lot of requests since that shutdown.
Okay, cool.
Another point of reference on the jobs front is the reports for, at least for Massachusetts anyway, the revenue for income taxes is up 3% year over year. So if they're getting more revenue, people are working.
Yep. So I'm going to jump in because this conversation is actually really, really interesting, but it's like the middle of the night, literally for Gunnar. So I'm gonna say, Gunnar, why don't you take it away, grab the screen share, and off we go. And let us know if you want people to ask questions during or hold them.
Yeah, no worries for me. Keep the conversation going.
Que me quedó de lo que compré en Kennedy.
And if everyone else can mute, that would be awesome.
Tienes activado eso.
All right. Now I'm sharing. Yeah, so as Brian said, it's the middle of the night here in Sweden where I'm located. So the date is on the first slide is wrong for me. It's November 6th here now, since a couple of minutes ago. But hi, everyone, and welcome to Chaos Engineering for Serverless Applications. We all know that the kinds of applications we build today, they usually need to scale a lot to be able to handle potentially millions of users. And we need to have this global availability, and we need to manage a lot of data in our applications. And it should all respond in milliseconds and just work all the time. So that's a quite hard equation to manage. So that's why we want to talk about chaos engineering today. So as Brian said, my name is Gunnar Grosch, and I am a senior developer advocate at AWS. We are hiring, by the way. So I want to talk about how we can use chaos engineering as a way to build more reliable serverless applications. And I'm going to do that by first off, look at what chaos engineering is and how we can use it, and look at some perhaps common weaknesses that we can look for in our applications, and a bunch of different practical examples for us. There we go. All right, so that's the agenda, fairly easy. And just a note that the first parts of this presentation isn't specifically for serverless. So even though if you're not using serverless today, you can probably learn a lot from how we do chaos engineering. When we move on to the end of the presentation, we're going to specifically look at examples for serverless applications. And just short about me then, I have a background as a developer. That's how I started out just over 20 years ago now in the industry, and then moved on through quite a few different roles through operations, started working with cloud infrastructure, before starting focusing on AWS. So started out as an AWS user, then got involved in the AWS community as both a user group leader, before I got honored with the AWS Hero title, and now I'm part of AWS as a developer advocate. But I still work a lot with the communities, both in my new role at AWS, but also in the serverless community with organizing meetups and conferences and so on. And I have 3 kids asleep in the room next door, so perhaps we'll get some guests later on in the presentation. Let's see. But now let's jump into it. What is chaos engineering? Well, first off, this chaos engineering is not about breaking things. If you've heard about chaos engineering before, you've probably heard that phrase, that breaking things on purpose. And I think that's probably great from a marketing perspective, because it helps draw attention to the practice. So we can use that phrase, of course, but we have to agree upon that breaking things isn't the purpose with doing chaos engineering. One of the creators of what's known as chaos engineering today, Casey Rosenthal, he was previously at Netflix, where he created chaos engineering. He usually say that I'm pretty sure that I won't have a job very long if I break things on purpose all day. And that's really true, because sure, we do break things every now and then when we use chaos engineering, but the breaking part isn't the purpose. Learning about the application and how it behaves, that is the real purpose with chaos engineering. And I talked about Netflix shortly. They are often used as the reference for chaos engineering. And chaos engineering isn't only for big streaming companies. That's also something that can be an obstacle for people trying to introduce it in their organization, because Netflix uses chaos engineering in production. Several other big companies do that, but chaos engineering isn't only for production environments. We can use it in test environments, in dev environments, staging environments, and so on. The more production-like the environment is, of course, the better. But there are a bunch of major companies today doing chaos engineering and doing it successfully as a way to help them build more reliable applications far away from production for several reasons. So chaos engineering is not only for production. And now then, I talked about Netflix once again, that chaos engineering isn't only for these big streaming companies. They are the reference used over and over again. Because they started what's called chaos engineering today. And looking at the companies that are doing chaos engineering today, well, it's from the small startups to these big companies like Netflix and e-commerce companies, and companies like Amazon is a great example of companies doing chaos engineering as a practice to help build more reliable applications. So looking at the data for companies that are hiring roles with the responsibility to do chaos engineering, that has spiked for, well, the last 2, 3, 4 years now. We see companies hiring SREs, they're hiring chaos engineers as well, people that have the responsibility to do these types of experiments to build more reliable applications. And we can't really have a chaos engineering presentation without having this slide as part of it. And the principles of chaos.org, it's a website that was created alongside the first book on chaos engineering, created by people from Netflix. So chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. So when we read that, I think it's clear that it's less about doing things that are chaotic, and it's more about experimenting. So the chaos part in the name chaos engineering, it's actually more about what we already have in our system, the inherent chaos that we have in the complex systems that we build today. So let's break this phrase down a bit. So chaos engineering is about performing controlled experiments to inject failure. And when we talk about experiment, it makes it sound quite scientific, and it really is scientific the way we approach chaos engineering. We create these controlled experiments, and then we measure the result from the experiment we perform. And some compare it to a vaccine, which perhaps is a great comparison these days, in that we inject failure, and in the end, we want to make our system stronger. And also, chaos engineering is about finding the weaknesses in a system and fixing those weaknesses before the system breaks. Because no matter how much we focus on making our system resilient to failures, there are always these unknown factors that come into play. We have different traffic patterns, we have our third-party dependencies or APIs, we have different network issues, we do a lot of code deploys, we make configuration changes and so on. So by doing the experiments and measuring the result from them, we're able to draw out these weak points, finding those in our system. And when we find those, when we fix those weak points, well, it should help us avoid that big outage. And we know those big outages never happen at the right time. But also very important is that chaos engineering is about building confidence. It's about building confidence both in the system and how it works, but also building confidence in our organization. Because when we do these experiments, we learn a lot about how the system behaves. And when we know how the system behaves, we build that confidence. But when we talk about resilient systems, a system that is resilient, a key part of that is the people that manage the system, that build features or operate the system. And by building confidence in those people, the people that actually run the system, we're able to gain trust and actually know more about how our system behaves. So every time we perform these chaos experiments, we learn new things about our system. So that's briefly about what chaos engineering is and what it's not. So we now seen that, hopefully you've seen that it's a lot more controlled than just breaking things in a chaotic way. So let's look at some of the motivations behind doing chaos experiments. So why should we invest both time and effort in doing this? So we often say that nothing on the internet is free. So no matter if we run an e-commerce site, an ad-driven blog site, or a big SaaS solution, if we have downtime or if we have issues, it's probably going to cost us money somehow, either in decreased sales or just by users not wanting to use our platform. And what happens the time the incident is there? Are we confident in that our monitoring, our alerting will actually notice that there is an incident? So will our on-call, for instance, get that page they need to be able to start engaging with the incident? And we all who build systems probably have these runbooks or playbooks, things that describe how we should act when we have an incident or when we have an outage or a problem with our system. But the question is if our organization actually is ready to handle these types of outages. Most of us probably do, or hopefully do, fire drills so that we know how to act in case of fire in the building we're in. But are we doing fire drills for incidents, learning how to act when we do have an incident? And every time there is an incident, we have this huge opportunity to learn a lot about the conditions that exist for that incident to be able to take place. And just to be clear, we're going to have incidents. We can't choose not to have them. So what about learning from incidents, but incidents in a controlled manner? And for me, perhaps the most important metric in any system that we have, happy users. So are our users getting the experience that they should, or are our users unhappy? And that brings us to the one that I perhaps see as the greatest motivation behind doing chaos engineering. Don't ask what happens if a system fails, ask what happens when it fails. Because a resilient system, it isn't one that does not fail. It is a system that maintains an acceptable level of service in the face of failure. So what happens when the system fails? Well, chaos engineering is there to help us reveal that. And lastly then, if nothing else I've said so far is motivation enough to start looking at chaos engineering, this is a statement that is from the updated reliability pillar of the AWS well-architected framework, the framework most of us perhaps use when we build our applications on AWS. It says that chaos engineering should be done regularly. So that's part of the AWS well-architected framework, the reliability pillar these days. AWS believes that chaos engineering is important to be able to know how our applications behave. All right, so we've looked at what chaos engineering is and why we want to do it. So now let's look at how we run chaos experiments. The more fun part, perhaps. So we're going to do this by following some simple steps. These are steps that we usually use when we create and run our chaos experiments. And the first one is that we need to define what we call the steady state. And the steady state, that's the normal behavior of a system over time. So it's ups and lows, it's highs and lows, it's ups and downs, the way our system normally behaves. And to find this steady state, we use system metrics, for instance, number of instances, CPU levels, and so on. And also we use business metrics. And business metrics, those might be number of active users, number of searches, items put in cart, and so on. And the business metrics, well, they are usually a lot more useful for us. Thinking about one of the motivations I said before, happy users. Well, happy users, they don't really care about how many instances we have or what the CPU levels are, but they care about being able to search, they care about being able to log into our platform. So using the business metrics to define our steady state is usually a lot more useful. And it's important to remember that the steady state which we talk about, it's usually not continuous in that it differs based on the day of the week, the time of the day, or day of the year, perhaps. Think of Black Friday as an example. So we define this steady state and we look at it, revisit it to define it again every time we create or do our experiments to know how the system is supposed to behave at this time. And then when we have that steady state in place, it's time to create what we call an hypothesis. And hypothesis, well, that is a proposed explanation that we've made based on limited evidence, something that we can use as a starting point for further investigation into something. And to find this hypothesis, we use what we call what ifs. We ask questions about the system. What if the primary database goes down? What if there is latency in our Lambda functions? What if Bob isn't in the office today? And when we create this hypothesis and when we ask these what ifs, we should remember that the chaos that we talk about, the failure injection, it can be injected at any layer of the stack. So infrastructure level, the network level, or the application or code level, or at the human level. What if Bob isn't in the office today? And when we create then the hypothesis based on these questions, we use the scientific if-then method to form it. So what if the database is down? Then we create a hypothesis. If the database is down, then we'll move to the fallback. If Bob isn't in the office, then Natalie will handle the issue, for instance. When we create these ask what ifs, we create the hypothesis, it's really common that we end up with an hypothesis that more or less tells us that there will be an issue. And when we do that, well, there's no real point in doing the experiment because we've already learned something about the system. we've already found out that if the primary database goes down, then everything will stop working. Well, time to fix that then before we create an experiment and do that experiment. Once again, the purpose with chaos engineering isn't to break things. It's about learning about the system. So always fix those known problems before you create an experiment. So next up then, we plan the experiment and then run it based on the hypothesis that we've created. So we gather people in a room usually, or in a Zoom call, and we then whiteboard the experiment. Try to find out how can we actually do an experiment around this hypothesis. If the primary database goes down, then we'll move to the fallback. Well, then we need to find a way to actually take down that primary database. And remember, we don't have to do it in production. We can do it in test environment or staging environment to then be able to prove or disprove our hypothesis. And this is usually a great place to learn as well. We gather people that know things about this part of our system, and we talk about how we're able to create this failure injection into our system. So this might be people from different service teams or from different parts of the organization. So a lot of learning usually takes place in this stage as well. And when we create our experiment, we usually want to maintain a small blast radius. So make sure that the chaos experiment that we create, it's the smallest possible one to begin with. So perhaps removing the primary database for all users, that's not a good experiment to start with. But if we're able to instead remove it for a small subset of users, only have a blast radius that affects 1% of users, or users from Norway, for instance, well, that means that we have a smaller blast radius for our experiment. And then as soon as we grow confidence, we know that we've proven our hypothesis, then we'll grow that blast radius. And of course, when we do our experiments, it's important that people know what we're going to do. Even though we're not doing it in production, if we're doing it in test or dev environment, it's a good thing to make sure that people know what we're going to do, why we want to do it. Because doing these experiments, even though the purpose isn't to make things break, well, it does happen every now and then. And having teams that know what we're going to do and why we're going to do it makes it easier to be able to do that next experiment when you want to grow your blast radius, perhaps. And of course, an important thing is to have that stop button ready. So you have one way of aborting the experiment, frankly. So you're able to, if you, for instance, remove that primary database, well, you need to have a quick way to get it online again so that you're able to stop the experiment if you notice that things break. Or after a while, when you've proven your hypothesis, you did move to the fallback. And the next step then, we've now planned our experiment and we've run the experiment. Now is the time to then measure it and learn from the experiment. So the metrics that we set up initially when we defined our steady state, those are metrics that we're now going to use to then prove or disprove our hypothesis. We remove the primary database. Did we actually move to the fallback, or did users have issues with the platform? And the key question to ask basically is, was the system resilient to the injected failure? We injected failure of some sort, and was the system resilient enough or robust enough to handle the failure we injected? A question that we usually have as well is, did anything unexpected happen? Because we create these experiments and we try to define how the experiment is going to play out, but there's usually these unexpected things that happen. And unexpected things might be negative kind, of course. We find these new dependencies. We created an experiment that affected service A, and we noticed that service B got affected by the experiment without us actually knowing that that would happen. So that's an unexpected thing. But also unexpected things can be of the positive kind. When we create an experiment, we find these unknown sources of reliability, resilience, and robustness in our system. We create an experiment and expect something to happen, but the system is able to withstand that failure in a way that we didn't anticipate. So those are positive unknowns for us. And then, of course, it's important to share the progress and let people know what we've done and what we found out. And this usually is a great way to get more teams, more people involved with the process, to be able to have other service teams perhaps, or other users in the organization take part the next time we want to do an experiment. So let people know that we did this experiment and we found this out. We learned these things about the system. So just to recap then, what we do first is that we define the steady state of the system, the normal behavior of our system with metrics and business metrics preferably. Then we form the hypothesis. If we do this to the system, then this is supposed to happen. And that's the thing we want to prove or disprove with our experiment. Next up, we plan the experiment and we run the experiment. We inject failure of some sort into our system. And then we measure and learn from it. And now when we've done this experiment, well, now we're able to then, based on that, either we've seen that things did break, so now we have things to fix. We have bug reports, we have these tickets, things that we need to do to improve our system. Or the system was resilient to the failure. Well, then it's time to take the blast radius we set before and perhaps increase it. So now we use 10% of users, or we include more Lambda functions, or remove more containers, for instance. And by doing this, by increasing the blast radius, we usually learn a lot more. Think about, for instance, adding latency to 5% of Lambda invocations. Well, that probably won't give the same effect as if you're adding latency to 50% of Lambda invocations. So by adding or having a larger blast radius, we'll probably find new things about the system, and perhaps things that the system isn't able to cope with as it did with a smaller blast radius. So now then, we've looked at how we can do our chaos experiments, how we look at the process to create them. So let's look at some examples of chaos experiments we can do for serverless applications. Because thinking about how we can do it for more traditional infrastructure, it can be fairly easy to create the experiments. If we run instance-based workloads, well, we can shut down instances. That's more or less how chaos engineering was started at Netflix back in the days. They randomly shut down instances, EC2 instances, to see how the system behaved when that happened. If we're running container-based, well, we can destroy pods or things like that. We can cripple network traffic if we have that infrastructure available. But with serverless, it is a bit different since we don't have access to that underlying infrastructure. We don't want to have it when we run serverless, but it means that to be able to do these experiments, to create the experiments, we need to be a bit more creative in the way that we do our experiments. But that's fun. So let's look at some examples. When we create the experiments, or I at least, usually look at some of the common serverless weaknesses that I see in architectures. So for instance, error handling. Are we handling errors correctly in our applications? So no matter if that's part of our code, we've written code to handle errors, or if it's part of a service as a feature in the service, I want to make sure that the error handling works as intended. And different releases from AWS, like dead letter queues and so on, they are great when building our reliable applications because AWS takes care of some of the error handling within our application. But I want to test those features. And doing that with chaos experiments, that's a great way to test it. And by using Lambda functions, and we use different services, upstream, downstream, and so on, having the correct timeout values is important for our application to work as intended. And usually we're able to set these timeouts correctly while we are within that steady state that I've talked about before. But what happens if there are issues in our application? For instance, if a downstream, a third party has an issue with latency in their system, how does our application behave then? Are our Lambda functions starting to time out and so on? And when we build applications today, events are becoming more and more important, and event-driven architecture is something that more and more are starting to use. So how we handle the events in our architecture is key in those type of architectures. So are we queuing our events correctly? Are we what happens to events if we have different type of service failures, for instance? And fallbacks. When we use a lot of services and a lot of third-party dependencies, it means that we trust those services to be there in our architectures. And looking at a typical serverless architecture, we have a lot of services involved. So what happens if a third party isn't there, for instance? Do we have fallbacks in place, or do we use graceful degradation, for instance, to be able to have these happy users once again? So those are some common weaknesses that I tend to look for when creating experiments to be able to test our architectures. So let's look at some on an actual architecture then. This is a really simple web service. We have a client calling API gateway. Behind that, we have two different AWS Lambda functions who are invoked by the API gateway. One Lambda function that stores or retrieves data in S3, and one who stores or retrieves data in DynamoDB. And we also have a bucket for, say, static content that the client can use as well. So we can inject errors into our code to be able to test that error handling, to see what happens if, for instance, our API doesn't return a 200 response. Instead, we get a 502 or 404. How does our application behave then? Or we can create exceptions within the code as well to see how those are handled. We can, of course, remove downstream services to test the way our application behaves if a downstream service is removed. In this case, it is S3, but it could of course, be any third-party API, for instance, as well. We can alter the concurrency of functions. We can restrict capacity of tables to test what happens if our application isn't able to scale the way we intended to. We can, of course, introduce different type of both security policy errors and configuration errors, because every time we change our application, either by adding new features, we create changes in configuration and so on, it is a way that we might introduce errors into our application. And these do happen. So creating these as experiments is a way to test how our application behaves if there are certain types of configuration errors, for instance. Some of us use disk space in our AWS Lambda functions. It might be for manipulating data, it might be for cache purposes and so on. And what happens if that disk space isn't available, or if we aren't able to store data to the disk space? For instance, files are larger than expected, so we can't really fit them in the temp space on our Lambda functions. Well, we can create experiments around this to see how our application behaves in those cases. And perhaps the most common experiment that we use is adding latency to our functions, because then we're able to simulate a lot of different failure scenarios that we sometimes see within serverless applications. We can also use it as a way to simulate cold starts. Even though cold starts is a minor issue for most today, with the improvements that AWS Lambda has had throughout the last few years, but it might be for certain type of architectures that cold starts affect the way the application behaves, not only on the first invocation, but also when we're scaling the application, when we're spinning up new containers for our Lambda functions. We can use latency to simulate different type of runtime or code issues as well, of course. we can use it as a way to add latency to our integrations, for instance, to downstream services or to, once again, third parties. And we can use latency injection as a way to test those timeout values that I mentioned before, to test what happens when we're not in the steady state. Do we start getting timeouts, for instance, in our Lambda functions? So these are some examples of chaos experiments that we can quite easily create within our serverless applications that will help us understand how our application behaves. And then on to how we do these experiments. Well, there are mainly two tools available for our Lambda functions today that we can use. One is Chaos Lambda, created by Adrian Hornsby, one of my colleagues at AWS. It's for Python runtime, and you're able to then create different type of failure and inject those into your applications. The other one is Failure-lambda, which is for your Node.js based Lambda functions, a library that I've created. And these have similar functionality, but for different runtimes then. So let's look at how Failure-lambda works. It is an NPM package that we install into our Node.js Lambda functions. And the configuration for Failure-lambda is done either through a parameter that we store in parameter store or through configuration that we use in AWS app config. And it has several different failure modes available that we can use. We can create these latency experiments that I mentioned before. We can create status code experiments. So get our Lambda functions to, instead of returning the normal 200 response through API gateway, we can inject any type of failure code, 404 or 301 or 502 and so on, to be able to test how our application behaves when we have those types of failures. We can create exceptions, of course. We can do those disk space experiments that I mentioned. And one of the ones I use perhaps most is the deny list one, where we're able to intercept network connections and then deny those. So for instance, Lambda is unable to connect to a third-party API or a downstream AWS service, for instance, to be able to test how our application behaves. And installing Failure-lambda and the Python version, it's fairly easy. We simply wrap our Lambda handler with the library when it's installed, and then we have the configuration, as I mentioned, as a parameter. Basic JSON syntax where we're able to enable, disable, and then configure it. So let's look at how we can do some basic examples of chaos experiments. And we're going to do that by using this simple serverless website, the Serverless Chaos demo site. It's a basic web service that's using a small serverless architecture. And the architecture is similar to the one we saw before. It just has 3 different Lambda functions instead. And what happens is that the client will every 5 seconds call API gateway to get an item from DynamoDB. And the 3 Lambda functions, they all fetch an item from DynamoDB at random and return that back to the client through API gateway. And the item that is returned contains a URL to an image that is then fetched from S3. So very basic application. And based on that, then we're able to create some different chaos experiments. And if you remember the second step in the process when we create our experiments, it is around the hypothesis. So let's ask some what ifs. What if my function takes an extra 300 milliseconds for each invocation? How does the application behave in those cases? What if my function returns an error code? So instead of getting a 200 response from Lambda through API gateway, we'll return an error code instead. And what if I can't get data from DynamoDB? So these are different what ifs we can ask for this application. And then based on that, we should then create our hypothesis. And if my application or if my function returns an error code, my application will use graceful degradation, for instance, return a cached response or something like that is probably how I would form my hypothesis. So with those what ifs in mind, let's move over to the demo. So here we go. So that's the serverless chaos demo site. I am pretty good with naming things, so it's quite clear what it is. So these are our 3 Lambda functions, function 1, 2, and 3. Right now, they're all returning 200 responses, and they are fetching new images every 5 seconds. And remember, the client calls API Gateway, invokes the Lambda function, fetches an item from DynamoDB, and then returns a URL to a new image. So that works as intended. Now, let me find the console. There we go. So these are the 3 Lambda functions. Let me just show you once again how that is installed. So Failure-lambda is installed on all of these already. Let's scroll down. So there we go. That's Failure-lambda. And then basically, I've wrapped my handler with Failure-lambda. So that means that everything happening inside that handler is now something that I can use to inject my failure to. Then to be able to do my experiment, I then have parameters that I store in parameter store. So those are the 3 ones, parameter 1, 2, and 3, 1 for each function, so that I'm able to control them each at once, or each, not at once, one at a time. All right, so there we go. So this is parameter for function number 1. It is JSON, as I said, and right now we can see that it is disabled. And for function number 1, I want to do the latency what if. So I've set the failure mode to latency, and I've set a minimum latency of 100 milliseconds and a maximum latency of 400 milliseconds. So it will inject something between 100 and 400 milliseconds. And that's everything I need so far. So just enable that experiment. Set it to true. Save my changes. And then switch back. All right, so looking at the site right now, we can see that function number 1 is still returning a 200 response. It is still loading new images, but it does take a bit longer for each invocation. We were previously at around 200. Now it's 400 milliseconds and so on. But in this case, well, it looks like adding latency didn't really destroy my application. It still works as intended. All right, so if I continue to add more latency to it, for instance, perhaps I would get another type of failure, or I would get a failure. At a certain point, I would reach the timeout value for my function, and the function would start to time out on certain invocations. And then, well, we could see how does my application behave in those cases. But really easy way of adding latency to each invocation of my Lambda function. So let's then look at parameter number 2. That's also disabled for now. And the second what if was, what if my function returns an error code? So in this case, I've set the failure mode to status code. And I've set the status code to a 404. So meaning that for the invocation, it will return a 404 instead of a 200. And as we know with synchronous Lambda invocations, in this case through API Gateway, the error handling, that's handled by the client. In this case, my web application, the front end. So the error code that I'm injecting in this case, it will be returned to the clients. So any type of error handling should be handled there. So let's enable this. But I'm going to do an additional thing. I'm going to change the rate of this failure injection. Instead of having rate 1, meaning that it would inject failure on every invocation, I'm going to set it to 0.5, meaning that I will inject the failure on about half of the invocations. Saving that, switching back. All right, we can see already that the first invocation gave a 404, and it didn't load a new image. Let's wait 5 seconds and see what happens. I guess it was a 404 on the next one as well. Still a 404, all right. There we go, now a 200. So it will inject failure on about half of the invocations and give us, well, not inject failure on the rest. So it will give us the normal 200 response. And in this case, well, my hypothesis was that my application will handle those errors in a graceful way. I can say that it didn't. The user was subjected to the error message. It didn't load a new image. So that's room for improvement in the application. Perhaps think about using graceful degradation in the way that we could use the last successful response to show an image, or we could use a cached response, or have a fallback image, one that we fall back to every time, for instance. And then on to the third one. Parameter number 3, disabled. The failure mode in this case is set to deny list, because the what if was, what if I can't get data from DynamoDB? So we want to intercept and deny those connections. So let's set that to true. And my deny list in this case, it contains S3 and DynamoDB. So it will then deny all of those calls. And as we know, we have DynamoDB as a downstream service. So let's save that and see if there we go. Now we get a 502. And in this case, well, that is because my Lambda function is throwing an error. It's unable to reach DynamoDB and doesn't really handle that in any graceful way. So it just throws an error, which is then returned to the client through API gateway. So once again, the error message is sent back to the client. We don't handle the errors in any good way in this application. So once again, it's room for improvement of the application. Perhaps add a circuit breaker so that we're able to stop making these calls that doesn't work to the downstream service, or use graceful degradation, once again, with cached response and so on. In this case, it's something that we should improve within our Lambda function probably, so we can have a better handling of the error there. For function number 2, that was something that we perhaps need to improve on the front end side of our application, since the error is sent there. So these are 3 examples of things we can do to easily inject failure into our application to test how does the application behave. And in this case, well, my application wasn't really good at handling these errors at all. The applications we normally build, perhaps we have more error handling and so on built into the application to handle it. But doing these experiments then, well, that's a way for us to then be able to know that the error handling works as we intended to when we wrote that code, or when we created our architecture, used certain patterns for it. Right, so back here then. I want to show you an example of I'm not going to show you the entire demo of that, but I'm going to show you an example of how I sometimes use chaos experiments to improve on an application, or perhaps to test the improvements that we've made. In this case, a simple web service with a downstream service, let's say that it's a third party of some sort that we need to call with our AWS Lambda function. So the client calls API gateway, who invokes the Lambda function and then calls the downstream service. Well, in this case, the downstream service isn't really reliable. Every now and then there are issues with it. So it doesn't respond as it's supposed to do, or it gives error messages back or something like that. Well, then we need to improve the way that we use it. We still need to use that third party, but we need to improve our application. So we, for instance, add a circuit breaker to the application. So the circuit breaker basically means that instead of just continuing making calls to the downstream service when it doesn't work, we're able to open a circuit breaker and then stop making calls to the downstream service. Instead, we perhaps have a fallback function of sorts so that we're able to then use the last usable response or cast response or something like that. So that's a good pattern to use to be able to then make sure that even unreliable services will continue will continue to have a working application even with unreliable services. So by then, after we've added this, we're able to then create chaos experiments to actually test this, because if the downstream service is unreliable, well, to be able to test that might be quite hard. Let's say that they have issues every 30 days or 60 days. Well, then we don't really know if the improvement we've done works as intended until they have a failure once again. But by adding chaos experiments to these types of improvements, well, we're able to then, in a really controlled fashion, test the way that we've built or improved on our application. So that's something that I tend to do when I work with these types of functionality within a serverless application, to be able to test what I've actually built. So that brings us here. So what's next? What we've seen so far, it's basically one-off experiments that we can easily do without really that much effort. It's easy to do these experiments to test different parts of our application. And that's where we should start. We should start by doing experiments in that way. Find a service, find a part of your system that you want to test, and do those experiments there. But as we gain this confidence, we learn more and more about the system, we perhaps want to look at how should we continue with chaos engineering, and how are companies doing this today? Well, I had this quote up before: chaos engineering should be done regularly, something that was part of the reliability pillar of the AWS well-architected framework. But I actually cut that off a bit. It's actually a bit longer. And this is the full quote: chaos engineering should be done regularly and be part of your CI/CD cycle. And that to me is pretty cool. It means that not only should we do these experiments often, but we should do it more or less every time we deploy something to our application, our system. So have it as part of the day-to-day work we do, to be able to test and verify that our application works as intended. So let me just show you a quick example of how that might look. This is once again our simple web service. I keep using that example, but can of course be any type of serverless application. But this is an easy one to describe and look at. And I've added a simple CI/CD. We have code commit, we have code pipeline, and we have code deploy. That's an easy way to do it using AWS services. So then we have the same what ifs as before. What if my function takes an extra 300 milliseconds for each invocation? What if it returns an error code? What if I can't get data from DynamoDB? The same as before. Well, looking at this then as part of our CI/CD cycle, these are what ifs that we want to ask and we want to verify, even as we add new things to our application. So we can then do the things I just did manually. Enable an experiment and then disable it when we've seen that it works as intended. We can easily do that as part of our deployment, basically just updating a parameter and disabling that when we're done. So in this case, as part of the deployment pipeline, we just enable these experiments, and then we look at the result from the experiment. And we want to do this as automated as possible, of course, but this could, of course, also be based on how your deployment looks today. It could be something that's semi-automatic or perhaps even manual. But look at the results. You have your CloudWatch alarms, for instance, in place. Well, observe those. Look at what happens when you've added your experiment. Are they still okay? Are they still green? Well, great. After 10 minutes of bake time, we can disable the experiment, remove it from our application. Another way of doing it is, once again, the same what ifs. We have the same application and pipelines. But you remember I talked about earlier that we want to have a smaller blast radius. Well, what I did just now, it would inject the entire application to these failures. Well, we can use, for instance, canary deploys. So we can deploy our experiment to just part of the application by using canary deploys. So for instance, we enable the experiment to 10% of Lambda invocations. So that means that 10% would get the experiment enabled, 90% would still have the version where we don't have a chaos experiment enabled. And then by looking at the result once again, we have our alarms and metrics in place. We can then look at the result and either roll back the experiment, or we can then continue with the deploy. Disable the experiment, but continue with the deploy. And a third option that's perhaps my favorite one, same what ifs, same application, but we can use feature flags. So we deploy a new version of our application, and then by using feature flags, we're able to then, with better control, we're able to control the blast radius. So for instance, if we use a canary deploy, we know that will, since it's stateless, we will have it on 10% of invocations, but we don't know which 10%. But by using feature flags, we can control it, as I said before, only to users from Norway, for instance. So we enable this only to certain users or certain, well, whatever way we have of controlling how we want to roll out features. And app config, as I mentioned before, as a way to control your experiments, that's a great way to do feature flags as well in AWS and in your serverless applications. So, yeah, and this case as well, of course, disable the experiment when we've seen the result, and then continue with the deployment of new versions to more and more users and so on. How are we on time, Brian? I know I had an hour.
We're getting to that point.
Yeah. Should I show one more demo?
Sure.
Cool. That was my next slide. So let's look at the demo of a deployment that way then. It's fairly quick. Just need to find my correct window. So this is the Serverless Chaos demo Canary site. As I said, I'm good at naming things. So fairly obvious that this is for chaos experiments that we use with canaries. And sure, this is just one user on one web page, but let's imagine that we have one user 1 through 12 different users using this simple website that we had before. All of them right now, they're getting 200 responses and all is good. So now we want to roll out this chaos experiments to test that. I could now start a pipeline and we just wait, but let me do it manually so we're able to see what actually happens. Oops. There we go. Better if I show you. All right, so VS Code, and this is the application that we're using. It's built using serverless framework. So this is the YAML file for the application. And what I want to do then is to do this chaos experiment that I did before, but instead of enabling it through parameter store, I want to do it as a canary deploy. So I'm going to use a feature in the serverless framework, or a plugin rather, that's aimed for canary deployments. And if I did this as part of my pipeline, of course, this would all happen through code build, so I didn't have to do it manually. And the way I can easily do it now is to simply just have two different parameters that I'm switching in between. So I have one parameter where the chaos experiment is disabled, and that's the one that my 12 users are using right now. So they are not subjected to the failure injection. And then I have one where the failure is enabled. And I have it set to status code. I'm using status code 502. So to do this experiment then, well, I just need to kick off my deployment, but instead switch it over to enabled. So let's deploy. Deploy that in Dublin. And what happens now is that the serverless framework and that plugin takes care of the canary deployment for me. I could, of course, use AWS SAM for this as well, which has support for canary deployments as well. And what happens in the background is that it will, first off, of course, do some CloudFormation magic for me to be able to update the stack. And then it will, seems too good to be true. Yeah, it was too good to be true. It will kick off code deploy for me to do the actual canary deployment to AWS Lambda. So that takes a few seconds. So in the meantime, let me just continue talking with you. So what it does is that it will kick off code deploy and then deploy to, I never even showed you, it will deploy to 10% of Lambda invocations. And if all is good, it will continue with the 90% that's left over 5 minutes. So now I believe we should, there we go, we are in progress. So code deploy has now done the pre-deployment validation and has started traffic shifting. So 10% will now get in the new version, the replacement version, that the only difference is that it has the experiment enabled. So looking at the site now, let's see, there we go. We can see that we're starting to get 502 errors, the error code that I injected into my Lambda invocations. But this also shows what I said before, that we don't have any control over where those invocations are. So more or less, well, every user can be subjected to the failure. I don't have control over which user will get that failure. So the blast radius, even though it's 10%, it's still all users in this case. But now, based on this, I would then have a CloudWatch alarm, for instance, set up to be able to monitor my application to see that it still works as intended. If the alarms go off, which they probably would since we're getting errors on the site right now, we could then stop the canary deploy and roll back because we want happy users, and we don't have happy users if they're subjected to errors usually. So that's a simple version of how we can do canary deploys of our chaos experiments. Then as part of our CI/CD. So then, in summary then, we want to use chaos engineering as a way to find weaknesses in our system, and finding those weaknesses and then fixing those before they create outages in our system. And we use chaos engineering as a way to verify that our system behaves as intended. When we create the system, the architecture, we set up patterns, we create code, we believe that we'll know how the system behaves. But by doing these experiments, we can verify that the behavior is as expected. And we do chaos engineering to build confidence, both in how the system works and in the organization. so that I, as an engineer, can be confident in that what I've built actually works as intended. And chaos engineering is something that we should do regularly, because we add features, we change things in our application. So the thing that worked and that we had confidence in 2 months ago might not be the same today. So do it regularly. And it is really easy to get started. The experiments I showed now, you could easily start doing those right after this call if you wanted to. And you don't have to do it in production. Important to remember, you can do it in dev, in test staging and so on. You'll still learn a lot about how your application behaves. And if you want some more, well, start off with the reliability pillar, of course. That's my go-to guide for everything around reliability and AWS. The Serverless Chaos demo app is available if you want to try it out, if you don't want to do it within your own applications. Failure-lambda and Chaos-lambda are, of course, available, open sourced. I mentioned Circuit Breaker, and that's also a package you can use to build your Circuit Breaker functionality within your application. And my good friend Jason has created a Serverless Chaos lab that you can do to do experiments and then look at how you can improve an example application that he has within that lab. So we've now looked at chaos engineering, what it is, how we do it, why we want to do it, and how we can use it to help build more reliable serverless applications. And with that, I want to thank you for joining me. And are there any questions, perhaps?
Thank you so much. That was amazing.
Thank you.
Anyone got questions? Jump in.
Hey, Gunnar, thank you so much. This is Tony. I have a quick question. When you add a latency, you just add a delay, or actually you have some way to inject the latency?
Since we don't have control over anything below the code level of the Lambda function, what we're doing is just adding a delay. That's right.
Okay. Yeah, I just guessing because I also work in Lambda. That's I couldn't figure out how you're going to inject latency in there.
No, no. So right now we're doing it as just adding a delay within the code. That's right.
Okay, thank you.
Is this a hypothetical kind of exercise, or is this something you're actually doing in your kind of day-to-day? Like, I mean, so this is a demo that you showed to us, like how the person can do it, but
yes,
can you maybe, like, well, what can you talk maybe about the actual, I guess, learnings that you did, really applying, this framework?
Yeah, of course. Well, this is definitely something that I've used when I've built serverless applications for the last few years. And for me, it started out as, well, since I have a background in more traditional infrastructure, moving to serverless was great because it meant that I didn't have to care about a lot of the underlying infrastructure. So, but still, even though I built applications using serverless, we still had failures every now and then. And the failures were unexpected, things we didn't really anticipate. So started doing these experiments and being able to then find those failures. So when we created a new feature, for instance, we did experiments on that specific feature or that specific service within our application to test that it worked as we intended it to. So had it as a way to then to basically verify that our application behaved as we wanted it to. So that's something that I've used for time flies. I guess it's a year and a half now, something in production built systems.
Yeah, maybe another question from me. So, when you do serverless, do you follow any like a traditional test-driven development, or you can apply that principle?
Yeah, my background before I started at AWS now was working for an AWS partner. So we helped many different customers build using AWS. So it depended on if we were the only party building the application or if we were part of a bigger team. So the way we worked depended on that. So it was dependent on the customer we worked with, but we still do the different traditional testing. So we still work with unit tests, integration tests, and so on. This was an added additional way of then working with the application more or less when it's done or when it's in production, even though we didn't always do it in production. So chaos engineering started out as a practice that was aimed as a way for testing, but more of a proactive testing for the things you've built.
Yeah, I found that like for the traditional unit test, kind of hard to do the serverless. You have any suggestion to that way or?
Well, that's a good question. Well, perhaps I don't have any good suggestions there, but I know several people say the same. I don't think I'm the right person to answer how to do testing, to be honest. That's not my strong side. But there are, yeah, I understand what you mean by it might be hard to do unit testing.
Yeah, thank you. I know I kind of struggling on that side. You see how to really achieve that.
Well, I mean, maybe I'm not following your question exactly, but for like a Lambda function in particular, I mean, you could run an entire Lambda function either deployed in Lambda or locally, because it's nice, it's modular. You have an event that comes in. So often what I'll do is I'll capture, for my early tests, I'll just capture into a JSON file the events that come in. I build some test vectors for those, and then so you have something that has a good, clear input and output, and so you can just kind of test the Lambda functions are amenable to testing with unit tests locally.
Yeah, it's you could like for the unit test, you could do a little bit more. Instead of you just reading JSON, right? So, but we can take offline for really good tip. Yeah.
Gunnar, your examples in this were using, and I understand that for the demo, you kept it relatively simple, but you were doing like one operation, one variable kind of binary failure, so to speak. This seems like something that you would do in some sort of combination running Monte Carlos or something similar, where you vary your inputs and you're looking at what happens when you have combinations of failures. And so do the frameworks help you with setting up those kind of combinatorials and variations on, is there a threshold at which the delay becomes too much, and I'm just using that one because you had that example, but there may be other variables that, it's something that you need to dial across a scheme, and when you get two and they cross, they hit a combination, then everything blows up kind of a thing. Is that something you've worked with? Is that something that people look at, or is it kind of one piece at a time?
No, I'd say that you can do it several different ways. One is to look at it one piece at a time to test smaller parts of a system, but the way that perhaps is the most rewarding one, it is to look at the bigger picture, to look at the application, since we want to verify the things that's important for the customer or the user of the system many times. So testing, should I say, to make these experiments as part of, to test the actual way the system should behave. For instance, recently did an experiment using a system that uses asynchronous invocations, but it receives quite a lot of events in the system that it's processing and so on. And by doing experiments on that system, we were able to find weak points in the system, not only in like the smaller examples that I showed right now, but in the entire system, the entire throughput of events through that system as quite large architecture, processing events and then storing events in this case it was in DynamoDB. And to be able to do that, we didn't do it in the production environment. We had to do it in a staging environment. So then we had to also, of course, have events pushed through the system to be able to test it. So we set up a way to create the events to be able to replay traffic that was production-like in the system to be able to test it in a correct fashion. Because otherwise, without having that production-like traffic in the system, we would never get the same type of behaviors by introducing these failures.
So I had a question that was actually pretty similar in the sense that especially if you're doing some kind of lights out CI/CD, or something at some load, you may get a whole bunch of different failures that correlate with some particular combination of perturbations that you've done in your test setup. What have you done, or what's available to essentially get a report? Like a whole bunch of stuff happened, errors happened, but I wasn't looking at the puppy dog to see it. So I want to be able to see, oh, when latency hit this threshold, and I had this database was out, I got this error. So to really kind of get the intelligence out of it, is it a lot of just looking at logs, or is there some tooling that you typically put together to try to bring out the information?
No, I'd say that observability is of course very important, so that you're first off is able to have that steady state in place, that you're able to know how the system should behave, and I suppose you could use more or less any type of observability tool that you're using today to do that. Simply looking at metrics will probably not give you the entire picture. As you say, having error logs available and so on is something that will probably give you more in that sense. If I look at the type of experiments or ways we've used this in the past, from my point of view, since I've worked with a wide range of different customers, the tools that we've had available has in many cases been set by the customer. So we've used the different type of observability or monitoring tools that they've had in place. And in some cases, well, it's basically CloudWatch and X-Ray to be able to monitor or observe what happens in the application.
So that's interesting. Another way to answer that is to say, if you have the problem I described, maybe it means that your fundamental observability isn't good enough. And so therefore, that is one of your learnings. You should fix your observability so that as you perturb the system, it's really obvious when something's breaking.
Yeah, that's a good point. Having observability into the application, I think in many cases it's something that we perhaps think that we have, but we perhaps don't see that we're missing observability until there is an issue that we need to dig deep to be able to find. And yeah, that could definitely be an outcome of doing these experiments, that we see that we're not able to see where the issue is or what actually happened.
Yeah. Gunnar, I had a thought. Another type of error to inject is a lot of times there's reachability and timeouts and so on, but there's also bad data. I was wondering about the notion of taking taking a message that your Lambda gets and just mucking with the context the context parameters and just seeing what happens when it or bad data in a Kinesis data stream. Just
manipulating data or events, that's something that I know it's quite common in other chaos engineering experiments. I myself haven't done that much in regards to serverless, but it is something that's used by, I believe, some of the other tools for more traditional infrastructure has support for that. So
yeah, I mean, I remember there used to be I think back in the C++ days, there was a tool that would randomly muck with your code and hope that you got a different answer.
Yeah, I think that it borders to other testing methods as well. Fuzzing perhaps is part of that. So
yep,
there is this gray area in between chaos engineering and more traditional testing methods.
Sure, sure. And I'm noticing the time. I want to do our contest before we lose people. So if you've been to our meetups before, you know that I generally ask questions about Battlestar Galactica or Firefly, and people sometimes like that, and Jen and Ken usually give me some grief about that. So I'm going to try a totally different one. What, Jen?
I have a good question if you're needing a question.
No, I have what I think is an awesome question.
Okay, go.
But and so the way this works is we're going to do one raffle. It's for the A Cloud Guru year license, and if you win, send an email to me, and I'll get you hooked up with it. I'm putting my at gmail.com, and you submit your answer in chat, and first one wins. Moving away from Battlestar Galactica to Lord of the Rings, what's the total number of rings of power in the Lord of the Rings?
I think we've got every number.
Nope. Yes. Daniel Sochor? Yep. The winner, it's 20. It's 3 rings for the Elven King, 7 for the Dwarf Lords, 9 for mortal men, and 1 ring to rule them all. So, yay. So Daniel, send me an email and I will get you hooked up with a very nice giveaway, I think. And Jen, you can save your question for another meeting, or you can just ask it now just for yucks.
Oh no, I'll save it.
Okay.
So happy with it.
Okay.
It's a good one.
It is.
Yep. Okay.
Gotta give people a reason to come back.
Yeah. What's the question?
So, okay. If we can ask, let's ask Gunnar. Is there let's let him go unless there's one more burning question.
I have one question.
Okay.
So in case of service mesh or microservices developed in Node.js or Java, how can we apply chaos engineering? Do you have any examples or links which you can share with us?
So how you can use chaos engineering with?
Service mesh.
That's a good
or I would say microservices which are developed in Node.js or Java.
And you're running, but
yeah,
are you running them in containers then, or?
Yeah, EKS.
Okay. Well, there are several tools out there available that you can use with containers today. The most well-known one is a commercial option called Gremlin. It is a SaaS solution that you can use, but there are a bunch of other options as well, both open source and commercial ones. And perhaps the the most known open source option is what's called the Chaos Toolkit. And the Chaos Toolkit is something that you can use with a lot of different services, and containers, Kubernetes is one of those, or some of those. So look into Chaos Toolkit, I'd say, is perhaps my tip, unless you want to go with a commercial option like Gremlin.
Okay, thank you.
Yes.
Okay, it's well into, I think it's past 1 in the morning for Gunnar. So I'd say let's thank you very much. This was amazing. And everyone in the Slack group should join the reInvent 2020 channel, and we'll chat there about if we want to do a panel during reInvent. And thanks all for coming.
Thanks, Gunnar. Great talk. Really interesting.
Thank you.
Thanks for having me.
And thanks everyone for attending. Come back next time.
Yep.
Thank you.
All right.
Good to see you all.
See ya.
Bye-bye.
Hello.
All right.
Say goodbye to people.